Hello everyone, welcome back to my channel. In the following two videos, I will show you how to do a DFT+U calculation on nickel monoxide. So as you may know, that the standard DFT faces some difficulty when calculating transition metal compounds and lanthanides. The reason is that standard DFT usually delocalize the electrons too much. But the let's say transition metals and lanthanides, they usually have localized magnetic moment. So that causes some difficulty. And then the standard DFT usually underestimates the band gap. One way to solve the problem is to add another Hubbard U term on side. So that's something that we want to show here. So I will split it into two videos. The first video I will show you how to do a standard DFT calculation on nickel oxide. And then I will show a DFT+U calculation on nickel monoxide, and we will compare it with the experiment. Okay, so let's get started. So I have already done the calculations. Let's say basically is a density of state calculation. Yeah, maybe you are already familiar with it. The first step is the self-consistency calculation to calculate the wave function. The second step is the non-self-consistency calculation for denser K points, and the third step is the density of state calculation to give you the actual information on the density of state. And the fourth step is to plot the density of state. Okay, and then let me walk you through the input files. Everything else is quite familiar with you, and the Bravais lattice is 5. So this is a trigonal lattice. You can look it up in the input file of the pw.x, and just believe me that those parameters together with those defines FCC lattice of nickel oxide. So nickel oxide is a FCC lattice. The reason why we write it using this weird way is that, as we will see in the following, that we want to define antiferromagnetic order of this nickel oxide. So the nickel atoms actually have different magnetization. So then we want to separate the nickel atoms, and we want to preserve the magnetic order, and then we also want to have the fewest atoms in the unit cell to simplify the calculation. So it seems that this is the best choice. If you are not convinced that this is a FCC lattice, you can open it in the X-Kristen to check whether this is a FCC lattice. Okay, so here there are 4 atoms in the like 4 atoms in the unit cell, and 3 type of atoms in the unit cell. Notice that here we only have nickel and oxide. The reason that why we split nickel into 2 types is that we want to specify a different magnetization on these 2 kind of nickel atoms. So this is quite useful when you want to do a calculation of antiferromagnetic order. So you just split it into 2 species and name it whatever you want. And yeah, okay. So n spin equals 2 means that we want to do a spin polarized calculation, and this is ultra soft pseudopotential. So E cut rho is more than 8 times larger than this E cut WFC. So here is like 10 times. And for the spin polarized calculation, you need to specify the starting magnetization of the first type of atom, that is the first nickel atom, to be 0.2. Just don't worry, you can choose any other number. We just here it is a starting point. The program will find the optimum magnetization during self-consistency. Okay. And then the second starting magnetization, that's the second atom, that is basically the second nickel atom, to be minus 0.2, because we know that it is an antiferromagnetic order. We specify that the direction of the magnetization is the opposite. Okay, And then the total magnetization is set to be 0. This is also because we already know that nickel monoxide is anti-ferromagnet. Yeah. So the number of bands we set to be 36. We increase with respect to the default value because we want to know some information about the conductance band. And the mixing beta, we decrease it to 0.3 from the default value because we want to facilitate convergence. Yes, and everything else, I guess it's the same as before. And to run the code, we use this command here. Yeah, I will not run it. It is also already run. And for the non-self-consistency calculation in the second step, most of the things are the same. Just add another argument here. Occupations equals tetrahedra. The reason why we can use tetrahedra is that this is basically a semiconductor calculation. This is not metal, so we can use tetrahedra method, and this method is very good for the calculation of the density of state. You don't need a super dense K point to already have a good density of state plot. Okay, and then we also increase the K points to 12 by 12 by 12. And the calculation, remember to change this to NSCF, non-self-consistency calculation. So, and then command looks like this. Yeah. And I have already run the calculation, and in the output file you can also see the Fermi energy here. Yeah, and then we want to calculate the density of state using dos.x. So the command is something like this, and the input file is you need to, as I said before, you need to keep the prefix and outdir consistent as the steps before. And this is the output file, and this is the energy window. So it calculates the density of state from 5 electron volt to 25 electron volt. And then this is the output, and this is the density of state file. And you see that is a spin porosity calculation. You have a spin up and spin down, and you also have the Fermi energy here. And to plot this, we can run this code here, and this is the density of state calculation. And you see that spin up and spin down is identical. The reason is that this is an anti-ferromagnetic material, so there's no real splitting of density of state. Yes, and then there are two things that I want to do. The first is to copy, is to basically screenshot and put it here as a reference. And then the second thing is to actually measure the gap size. So this is 13.76, this is 14.59. Okay, and then the calculation is 0.8227 electron volt. So in this video, I've shown you how to calculate the density of state of nickel monoxide using standard DFT, and the gap is around 0.8 electron volt. So in the next video, I will show you how to add a U-term, and then how the U-term changes the band gap. Okay, so thank you for watching, and I hope to see you next time.